Hi students, so 5.3 anti-differentiation by substitution, and to get us started and warm up I'd like you to start with some differentiation. So the three questions on the board, F, G and H, use your chain rule to differentiate those and see how quickly you can do them. Off you go. Okay, so you've practiced those questions with the chain rule. We're actually going to see the answers now. And the answers are exactly these three here. So you can check you're working out using the chain rule for F, G and H. This is what you should have got. And the reason we started off that way is because this technique, anti-differentiation, is the chain rule backwards. And we know this whole idea, anti-differentiation, always comes back to doing differentiation backwards. So let's think about how the chain rule actually works. When we write it out fully and formally, we introduce this dummy variable, right? And we call it u, and it transforms what we are trying to differentiate into something that is easier and that we know how to do. And in fact, with integration, it works out the same way. We use a dummy variable u, and it transforms the integrand, that thing we're trying to integrate or anti-differentiate, to something we know how to handle. That's the idea. So, in order to use substitution and to spot a substitution question, we're looking out for a particular pattern, just like how with the chain rule you look out for those patterns. What we're looking for is a function that can be split into two parts. And I call it a nested function because I mean a function in a function. So f of u, where u is another function itself. And the two parts we're looking for are a function of u and the derivative of u. And if we see an integrand that's those two things, and we can split it into those two parts, 1 and 2, well then we're away and we can use this technique of substitution. So the first thing we're going to do is try and spot these parts. And for these three questions, what I'd like you to do is pause the video and try and split each expression up into two parts, one of which is a nested function, f of u, and the other one is the derivative du by dx. Have a go at those, and then I'll show you what I mean. Okay, let's have a look at this. So for this first one here, if I say that u equals cos x, well then I know that the derivative of du is minus sine x, and I can see a sine x there, and this bit here I could say is f of u, which is minus u squared. And I need these two negatives here, if we think about it, so that they cancel out to give me an overall positive thing. So what I'm actually doing here, and that this is where these questions can just be a little bit tricky, is I'm actually rewriting this as minus sine x times minus cos x, which gives me the same thing, and I'm saying that minus cos squared x is minus u squared, and minus sine x is du by dx, and this works. In a second we'll go on to solve that. For the second one here, we're looking for this nested function, and I think I can kind of see it here. So the nested function of a function, is going to have u as x cubed minus 1. If u is x cubed minus 1, then du by dx must be 3x squared. And this almost balances at the front, right? So we've almost got du by dx times by a function of u, which is what we're looking for, But in order to make it work, I just need to balance the constants a little bit, like the last one. So if I write the function as 5/3 u to the power a half, then this is the same thing as du by dx times f of u. So for both of these, just to recap what we're doing here, f of u du by dx is sine x cos squared x. If I multiply these two things together, I get this. With this one here, if I multiply this by this and substitute in x cubed minus 3, I get the expression in the integrand, which is what we're looking for. So I multiply those two together, and I get 5x squared times u to the power a half. For the last one, for an exponential, what we're going to do is we're going to let u be x squared. Du by dx then is pretty simple. Du by dx is 2x. And to make it balance, this function divided by 2x, it's what's left over, right, is going to be 3/2 times e to the power u. So if you're struggling, a way to find the f of u is to, once you've found your du by dx, divide the original integrand by that. And that will tell you what's left as your f of u. If we divide the integrand by du by dx, it's going to tell you what to make f of u. And in this case, f of u du by dx, we can check it. These two multiply to give me the integrand, 3x e to the power x squared. So, why do we do this? Well, we do this because it allows me to change the variable of integration. Because if I have du by dx, we get this magical cancelling, and we can change the variable of integration from x to u. Instead of integrating over x, or with respect to x, we integrate over u. And that allows us to integrate the simpler function f of u, not the complicated function in terms of x. So let me show you how that works. Same examples. I'll do the first one and then you can try the others. I define my integral I. Remember, we spoke about this being a good strategy to help you lay out your integration questions. And then what we're going to do is we're going to let u be cos x, because we figured out in the first question, like up here, that that was going to be our strategy. If I do that, then du by dx is minus sine x, and the integral is the integral of minus u squared times du by dx du, using what we were doing above with f of u and du by dx. Sorry, this should say dx here. Then this part, the du by dx, I can change to du. So now I just have the integral of minus u squared du. I've changed my variable of integration, and all of a sudden, this is actually an easy integration. This is minus 1/3 u cubed plus c. And because u is a dummy variable, at the end, we just substitute back in for x, and we have the solution to the question. So what happened here? Let's recap. We took something that was complicated and in terms of x, and we found a clever substitution that changes the variable of integration to make it an easy integration in terms of u. We did that easy integration, and then we substituted back in for x afterwards. I'd like you to use that same layout, that same idea, and the work we did up here to try these two questions. Pause the video, have a go, and then I'll go through them quickly. Okay, so you've tried these, right? You've labelled I as being 5x squared, x cubed minus 1 to the power a half dx, and you've said that u is x cubed minus 1, which tells you that du by dx is 3x squared. Then, that means that your integral has transformed to 5/3 u to the power a half times du by dx, which is the same as 5/3 times the integral of u to the power a half du, and we've changed a difficult integration to an easy integration. Integrating u to the power a half gives me 2/3 u to the power 3 over 2 plus c, always plus c. So that gives me 10/9 u to the power 3 over 2 plus c, or in other words, substituting back in 10/9 times x cubed minus 1 to the power 3 over 2 plus c. Hopefully you got that. If you didn't, try the last one again now. I. Start by defining I. 3x e to the power x squared dx. Always remember your dx. We let u be x squared. We decided that before, which tells us that du by dx is 2x. So, I is the integral of 3 over 2 e to the power u times du by dx, which is the same as 3 over 2 times the integral of e to the power u du. If we integrate e to the power u, we just get e to the power u. So overall, we have 3 over 2 e to the power x squared plus c, and that's our solution. Okay, so that's the idea, right? At every stage, what we're doing is we're finding a clever substitution which allows us to represent the integrand that we're given as the product of a function of u times by du by dx. And all of these colours correspond to what we've got above. So we find a clever way to write this as this product, which allows us to change the variable of integration and so turn a difficult integration question into an easy one. This question, the next part, gave you quite a lot of space for these ones. This next part gives you a clue as to what's going to happen here. So I'd like you to have a go at it. We're talking about inverse trig functions. We can see there's a square root here, and we can see it's positive. So we know we're going to be talking about sine inverse. Sine inverse, if we remember the rule, is 1 over root a squared minus u squared, and we know that that integrates to sine inverse of u over a plus c. So we're trying to take this and write it in this form, and then we know how to do it. I'd like you to have a go at that, see if you can figure it out, then unpause the video and I'll go through it. Okay, so you've had a go. You're trying to match to this form. So the biggest thing here is we need to figure out what's our substitution going to be. So I define my integral I, which is going to be 3 over the square root of 9 minus 4x minus x squared dx. And I can tell what's going to happen here. I'm going to use the completing the square idea, and I'm going to try and get the last part of this, the minus u squared, to be a neat perfect square. So I'm looking at the minus x squared minus 4x, and I'm thinking, well, this is the same as 9 minus x squared plus 4x. And to make this a perfect square, this is close to x plus 2 all squared, but that would give me a plus 4, and if I'm going to have an extra plus 4 in here, because it's negative because of the subtraction, I'm actually going to have to make it 13 minus x plus 2 all squared dx. If, as we work our way through this, we're unsure, well, then we can just expand this and we can check that we get the same values as above. But if I expand this, it's going to give me x squared plus 4x plus 4. That's all going to be negative. 13 take away 4 is 9. So it matches. So this is close to being in the form we want. We take the 3 out the front. We can say that's the same as 1 over root 13 squared minus u squared dx. Well, what is u? U is x plus 2. U equals x plus 2, then we need to look at du by dx. Du by dx is 1. So I can switch because this ratio, the derivative of u with respect to x is 1, that means du is the same as dx. And I'm just going to show you, in comparison to the previous questions, a slightly informal but powerful way to think about this. These aren't fractions. Remember, we always say that, right? They're not fractions, but we can think about them using our rules and notation of fractions, because it's a ratio. So in other words, when I do this, du equals dx, because du by dx equals 1. So taking that idea, I can change the variable of my integration to root 13 squared minus u squared du, because du and dx are the same in this case, which means I can integrate it to give me sine inverse of u over a, which is root 13, plus c, and then because that was a dummy variable, I substitute back in for x plus 2 over root 13 plus c. Sorry, lost you just at the bottom of the page there. It's my final answer. So, what did we do here? Well, we completed the square. We made a linear substitution. For a dummy variable. We then did an easy integration in our dummy variable, and then we substituted back. And in any similar question to this, with the inverse trig functions, where we want to use a substitution, this is going to be our strategy with these 4 steps. Okay, last little set of questions. So I mentioned there that what we did was a linear substitution. In other words, like u equals ax plus b. And the last thing we're going to look at is how those kind of linear substitutions can actually clean up really messy integrals that we're asked to complete. So I want you just to take a second and look at these expressions here and think, wow, all of those, if you were asked to integrate them, you would not be able to do that. Because we do not have a good method for integration of products. I want you to be really clear on that. If I ask you to differentiate these, sure, products rule, quotient rule, chain rule, that you could do this. But we do not have a process like that for anti-differentiation, for integration. And so, what we need to do is we need to do a clever substitution that's going to tidy these up and turn them into something we can integrate. And here's the trick. You take the bit that's messy, the root 3x minus 4, and we rewrite it as u to the power a half, where u is whatever it needs to be. In this case, 3x minus 4. For any linear substitution, because du by dx is 3, du is going to be k dx. Because the du by dx is k for some constant k. What that means is, this process of the substitution, if you keep it linear, it doesn't complicate your integration. Like, there's no problem with an extra constant, right? The constants are easy, you just put them at the front of the integral, doesn't make it more difficult. So, linear substitutions are actually never going to do any harm. They might, if you do it in a pointless situation, they might not do any good either. But a linear substitution is never going to do any harm, and in all these examples, it can actually turn something very difficult into something that you can do. So, I'd like you to try them just as normal. Don't wait for me to do it. The first two are okay. The last one's a little bit of a monster and will require your calculator at the end to simplify it. But have a go at them, and once you've had a try, I'll take you through. Off you go. Okay, so all of these are a little bit time consuming. I'll try and get through them quickly and clearly. So first one, what is our integral? Our integral is 2x plus 1, x plus 4 to the power a half dx. What's the messy bit here? The messy bit is this, x plus 4 to the power a half. So I'm going to let u be x plus 4, which tells me that du by dx is 1, which tells me that du equals dx, which is good to know. The other thing I need to figure out as I do this is what 2x plus 1 is in terms of u. And this is where I just need to be a little bit crafty and clever with my algebra. 2x plus 1, if I multiply both sides of this by 2, 2u is 2x plus 8, so 2x plus 1 is going to be 2u take away 7. Have a little think about that. 2x plus 8 is 2u, so 2x plus 1 is 2u take away 7. Just being a little bit agile with our algebra now gives me the ingredients I need. So 2x plus 1 I can change to the u form. This bit, x plus 4, I can change to the u form, and scrabbling around, where's my blue pen? The dx I can change to the u form. So for all the pieces, I can change them in terms of u, which means my integral is now going to be 2u minus 7 times u to the power a half times by du. And you might be thinking, well, what's the point of this? It's not made it that much easier. But if I expand this now, I've got 2u to the power 3 over 2 minus 7u to the power a half du. And you've noticed that this is something that we can integrate, that we have no trouble with. So, raise the power by 1, divide by the new power. 4/5 u to the power 5 over 2 minus 14/3 u to the power 3 over 2 plus c, always plus c. We substitute in x plus 4 to the power 5 over 2, x plus 4 to the power 3 over 2, plus c, and we are done. So, why did that work? It worked because the x plus 4 to the power a half is tricky, and we can't expand these brackets at the moment. But if I can change the tricky bit, so it's just u to the power a half, well then I can expand the brackets, I no longer have a product, and I have something I can integrate. That idea is similar in all these questions. So, part B. What's the integral in this case? The integral is 2x plus 1 over 1 minus 2x squared dx. What's the tricky bit? Well, the tricky bit is the quotient here, the denominator, the 1 minus 2x to the power 2. So we let u be 1 minus 2x, and then we try and work out the other bits that we need for our substitution. What is dx? Well, du by dx is minus 2, so dx is minus a half du. Think about that for a second. Multiply both sides here by dx. Du is minus 2 dx. Divide by minus 2. Dx equals minus a half du. So, just building this up bit by bit, because I know this is a new technique. I can switch the 1 minus 2x for u. I can switch the dx for terms of u. What's the last bit I need? I need the 2x plus 1. 2x plus 1 is, now looking at my initial definition here, if I make this negative, minus u is 2x take away 1. So I need to add 2 to that. It's going to be minus u plus 2. So 2x plus 1 is the same as minus u plus 2, meaning that I can use my substitution to switch all these things out. I have 2x plus 1, which is minus u plus 2. I'm going to write that as 2 minus u. 1 minus 2x to the power minus 2. That's now u to the power minus 2. And I have dx, which is now minus a half du. I clean all of this up a little bit. I bring the half out front. I change the minus sign inside my brackets here. This is going to give me a half of u minus 2 times u to the power minus 2 du. And where do I go now? Let me go up here. That means I equals a half of the integral. As I expand that bracket, u to the power minus 1 minus 2 u to the power minus 2 du. That's the integration I need to do, but I can do that. That's easy. U to the power minus 1 is going to give me log base e mod u. This integral is going to give me the 2 cancels with the half. It's going to be something like u to the power minus 1. If I do this, u to the power minus 1, I would differentiate. It would be negative, so the signs would match. The 2 cancels with the half. There's no other coefficient needed. That's good. This is my my result. Obviously, if you're unsure about it, always with anti-differentiation, you can differentiate your answer and check that it gives you what you wanted. But this is correct, and so the final thing is to substitute back in. Log base e of modulus of 1 minus 2x plus 1 over 1 minus 2x plus c, and that is my final answer. Okay. Last one, part C, and this is where we're done for this video after this point. What's my integral? Define it. X squared times 3x minus 1 to the power a half dx. What's the complicated part of this? The complicated part is definitely the power of a half, so u equals 3x minus 1. I now know how to substitute the 3x minus 1. I've also got the dx. So du by dx is 3, which tells me that dx is a third du. That's the second bit. Dx I can now change to be in terms of u. The last bit is x squared. Well, x is u plus 1 over 3. Just rearranging here. So x squared is a 9th times u plus 1 squared. And this is my final ingredient. I now have x squared in terms of u. So I can make my substitution. The integral is 1/9 u plus 1 squared times u to the power a half times 1/3 du. Substituting in for each of my parts, what am I left with? 1 over 27 times the integral of u plus 1 squared times u to the power a half du. And now, using the similar technique to that example we looked at earlier, I can do the expansion. This is u squared plus 2u plus 1 times u to the power a half du, and completing that, that's u to the power 5 over 2 plus 2u to the power 3 over 2 plus u to the power a half du, and this is something I can integrate. Fantastic. Doesn't mean it's going to be really simple. 1 over 27. Doing my integration, divide by the new power. 2/7 u to the power 7 over 2, plus divide by the new power. 4/5 u to the power 5 over 2, plus divide by the new power. 2/3 u to the power 3 over 2. We're going to do our final substitution in, and we're going to simplify it. And this is the bit where I said, it's a bit of a monster. You're going to have to use your calculator at this point if you haven't done so already, because the coefficients are going to be big. We're going to substitute in for u using the 3x minus 1. various different ways you can write it, but if you fully simplify it, what you'll see in the textbook is they look at all the coefficients, they expand the terms, and what you end up with, if you take out a factor of u to the power 3 over 2, is you end up with 135x squared plus 36x plus 8, and of course we must always remember r plus c. So that question's a monster, I don't deny it. That last bit is just algebra and it's ugly. But what I want you guys to practice today when you do this exercise is this idea of doing the substitution and swapping out all the things that are in terms of x for things that are in terms of u. And I've tried to make that clear with the colours and with my layout, and I'd like to see you trying to be as clear with it yourselves. I left loads of space for these because I knew they were big questions, but the last little thing that's here is there is, of course, your calculator at the end of the day. Everything we've done is a non-calc question, apart from that last little bit. You can be asked all of these in the non-calculator exam, and you will be asked to do an integration by substitution. I'm confident of it. But your class pad is helpful. If you make sure that you select indefinite when you do your integral, you make sure that x is the variable and you put it into your calculator like this, it will give you a solution. And this is the last question here, and you can see that it does that. You will have started to find out, though, and this is where you just need to be careful, the calculator quite often doesn't give you the neat solution. And that's where you need to be clever with the way you use it, you need to be smart, you can't rely on it, because quite often you need to be able to use your non-calculated skills to get the answer in the right form that they're asking for. Best of luck with the exercise today. The next couple of lessons after this are going to be about substitution as well. So we're going to continue to develop these skills, and let me know if there's anything that you're really struggling with. Best of luck. Speak soon.